And the screen is visible, right?
This meeting is being recorded.
Yep.
Okay.
All right, everyone. So welcome to this is our fourth GROOT seminar of the summer. So today we'll be hearing from Sandip Samanta about H-splitting in loop space fibration. So please take it away.
Okay. Thank you. So first of all, I would like to thank the organizer for giving me this awesome opportunity to talk on this. So as the title suggests, so I'll talk on H-splitting in loop space fibration. So I'll first go through all this term, what it means, from very basic. So let us start first with the uh, definition of H spaces and H maps, and then I'll go to H splitting. So H spaces is a space X. So first of all, topological space such that there exists a continuous map from X cross X to X. So one can say this is a binary operation, continuous binary operation on the space X, and there exists a point E in the space such that if I put in one coordinate E and then take the this map mu, it will be homotopic to identity in both coordinate. Then we'll call this X H space, and together like this three data, this identity, namely the homotopy identity, I would say. So this homotopy identity, this a continuous binary map, and this X, these three data totally as referred as H space. So like typical example of H space are topological groups where this multiplication map is continuous, and also topological groups already have identity. So this is on the nose, this is identity. You don't need any homotopy there between these two maps. And like we can consider any matrix group where with respect to multiplication, and in the sphere thing, so S1 already as a subspace, or like as a subset of complex number, there we have the usual multiplication, and S3 as quaternions, there is also we have a group structure. And other sphere, this S7 also has thinking that as a quaternion, so there we also have similar multiplication and this identity. So these are like typical known examples of H spaces. So other the most like we are mostly that interested in. So for any space X with a given base point, say X0, we can consider the base loop space. So which consists of all maps from 0, 1 to X, such that the so this is basically paths, and but the path start and ends at the this base point X0. So this collection is called as base loop space of X. So given any topological space, you can consider this space, and here you can actually multiply two things. So by a concatenation of loops, because the endpoints are all are like starting and endpoints all are X0. So you can take two loops and just concatenate those two loops, just speeding up those two loops. So we have a binary operation, and if I consider the constant loop at X0, then that will serve as identity in this case, homotopy identity. Okay, so these are these things are the like most interesting thing in this case. So we'll revisit this thing later on. Okay, so now defining these H spaces. So the first thing is that if I given two H spaces, let's say with these two structures, so x mu e and x prime mu prime e prime, and the map between those two, when it like how they are look like. So the map between those two are called H map if it preserves the identity element, and it is like almost like group homomorphism, but not exactly. Instead of the equality, we have this homotopy. So as a map, if I consider from x cross x to um, x prime. So these two map. First, you take the multiplication in x and then go through f to x prime, or you can take individual f cross f to go to x prime cross x prime, and there you apply the multiplication of x prime. So those two maps as a maps those from x cross x to x prime are homotopic. If these two conditions satisfied, then we call a map between two spaces as H map. Okay, so again the typical example of H map, or if I consider my H space as groups, topological groups, then group homomorphism are definitely satisfied these two conditions, and they are H map in this case. And similarly, again, if I consider two topological space X and Y and any continuous map between those two, then in the base loop space level, we have a induced map omega f from omega x to omega y, and that is always a H map. Okay, so the map is defined like if I have, let's say, gamma here, then I will just say like omega f of gamma is just f compose gamma. So that the induced map here, and this is like respect the respective concatenation map here. Okay, so now let's come to the fibration. So fibration is like usually denoted by like F to E to B, but this is inclusion. So it need not be always inclusion. We may like replace this fiber to some homotopy equivalent spaces, but usually we'll denote this as inclusion, and this E to B. Usually this E to B is the main part of the fibration. So by this we mean for any space X with the given this diagram. So basically this is a homotopy from X to B given this homotopy, and a lift at the zeroth level x cross 0, you have, suppose on the E level you have a given lift, then there exists a this whole homotopy lift to E. If such lifting exists, then we call this E to B as fibration, and this F will be the inverse image of the base point B0 in B. Okay, and so the trivial example will be if consider any two topological space and consider the Cartesian product of those and project onto any of this coordinate, then that will form a trivial fibration. With fiber you can think of it as like f, like the other coordinate which you project, the other coordinate than where you project. Okay, so another example you already might have seen, that covering spaces. So covering spaces already have this homotopy lifting property. So those are also fibration. Or more generally, if we consider any fiber bundle with this base space paracompact, then this homotopy lifting always exists, and that is actually due to this Swibus and Hurewicz. In general, if you have any fiber bundle, need not be this paracompact base space, but for those cases, you always have lifting for not all general spaces, but at least for CW complexes. And such fibration also has name as serif fibration. So this, if the homotopy lifting exists for any general spaces, then we call that as Hurewicz fibration. So that is in general named as fibration. And if the homotopy lifting exists for CW complexes, then you call that as set fibration. So any fiber bundle is actually set fibration, but to hold this as general Hurewicz fibration, you need paracompact base space. Okay, so the other example that also comes from comes immediately for any topological space. So you consider the path space. So it consists of all paths that start at fixed base point x0, and you consider the evolution map. So you just evaluate that that path at the endpoint 1. So that is also forms a fibration. And if I just take the inverse image of this x0 base point of x, then this EV inverse of x0 will be exactly those paths which start and end at x0, and that is exactly our base loop space, right? So this is a fibration, and its fiber is actually this omega x. Okay. Similarly, we can also consider the free loop space, so that there we don't restrict our this starting and end point to be x0, but any point. And so it consists of basically odd loops from loops in x1. So you can think that as a map from s1 to x, and again you consider the evolution at the 1 or 0, both are same, so they are that map, and that is again turns out to be a fibration. And here also again, if I consider the evolution on inverse of x0, then that is again the same fiber omega x. Okay, so now let's come to our case, which we want to like study this loop space fibration. So given any fibration, this f e to b, we can just take the respective base loop spaces with respect to the like fixed base point. So suppose if the base point here is f0, and the base point here also we consider as f0, that means I f0. So under inclusion, this also belongs to here, and the b0, the base point here will be p of f0. Okay, with respect to this base point, we consider the respective and these base loop spaces, and there we also have induced map this omega I and omega p. And as it turns out that if we take this b to be well pointed space, then this is on the nose actually becomes a fibration, and that fibration we call as loop space fibration for the given fibration, this f e to b. Okay, so uh, so in this case actually, if like it's good to mention that any map can be made into a fibration. Like if we by replacing this, suppose we are given suppose any map a from x to y continuous map, then we can actually turn this into a fibration by replacing this space x by some homotopy equivalent space. Okay, so even our this b was not well pointed, we can actually make that to be fibration, and still get this similar kind of vibration, and we refer that to be as our loop space vibration. Okay, so given like defining this loop space vibration, we like first ask that when this loop space vibration split, as our goal that uh, when this split. So splits means here that the total space, this omega e, that is homotopy equivalent to omega b cross omega f as fibration. So as fibration means actually like if we have a homotopy map from omega b cross omega f to omega e, and also this as a map, this is fibration, right? So I can consider omega f to omega b cross omega f and to omega b, and if this is a homotopy equivalence, let's say, and also we have omega b, and here we have omega f. So this diagram actually commutes at least up to homotopy. So then we call like that we refer as these splits as fibration. Okay, so and the answer is known due to Ackermann-Hilton, and it says that if there is a map gamma from omega b to omega e, such that this omega p compose gamma is homotopic to identity of this omega b, then then this this vibration splits. Okay, and this gamma actually, the which is here the homotopy right inverse of this omega p, is named as homotopy section of the vibration, and the particular map which is the homotopy equivalence is you just go like the natural map from omega b cross omega f. So omega b cross omega f, you go to using this gamma, and omega I, you go to omega e cross omega e, and there you use the multiplication map, like concatenation. This mu is the concatenation map in omega e, and to go to omega e. And this actually the like exact homotopy equivalence between this omega b cross omega f and omega e. Okay. So, but this at this point, so we have the homotopy equivalence, but this omega b cross omega f and omega e both had some extra structure, right? Because already we have seen this loop space already are H spaces, so they have the concatenation like multiplication on the space. So omega b cross omega f is, again, you can think of omega b cross f, or directly like omega b cross omega f, where there still also you have H space structure, and this is also has H space structure. So the next question is, when does this not only splits as fibration but also as H spaces, like the homotopy that we like homotopy equivalence that we had, this theta, that is actually preserves the respective H space structure. Okay. And that is not actually in general always happens. So for the example is due to Khalil Sajjad, and so the example is, you consider the this fibration. So here think this H2 as CP1 complex projective space in like one-dimensional complex projective space, and like include that in CP infinity, and you make that as, so that inclusion is not fibration, but you make that to a fibration, and by making that you will actually see that the fiber will be homotopy equivalent to the homotopy equivalent to S3, and then considering that as fibration S3 to S2 to CP infinity, there actually if I consider the this loop space fibration omega S3 to omega S2 to omega CP infinity, but omega CP like CP infinity is already like Eilenberg-MacLaurin space kg2, and if I take the omega of that thing, that is again kg1, which is again homotopic to like S1, right? So we actually have a fibration omega S3 to omega S2 to S1, and this fibration actually has a section, because this if I consider the H2 to H2 identity map and take the adjunction to get like we have a map from like this S1 to omega S2, like okay, so if I consider the identity map S2 to S2, then S2 I can think of suspension S1, and this if I take the this suspension loop space adjunction, so I have a map actually S1 to omega S2, and that will actually serve as a section for this fibration. So once we have a fibration using this Ekman-Hilton thing, we can say that this omega S3 omega S2 is homotopy equivalent to omega S3 cross S1, but this is not as H spaces, because here this S3 has H space structure, so it is also another like argument of like Ekman-Hilton, that if you have a H space structure, if you have any H space X, let's say, and then if you consider the omega of that thing, then that is actually abelian H space. So omega S3 is abelian, and S1 we already know this is also abelian. So the product thing is also abelian, but it can be shown that this omega S2, the concatenation map here, is not abelian, and that is also can be seen by seeing the like whited product there. So which I'll define later. So but this omega S2 is not commutative, homotopy, at least homotopy commutative also. So on the right hand side you have commutative thing, on the left hand side you don't have, so it cannot there cannot exist any H space map between these two. Okay, so the question is actually at least makes sense that you may have fibration splits as just as like homotopy, but may not preserve the those structure. So to answer those things, so Liu gave a partial answer to that, and it says that if you have a fibration Fe to B, if F has some already F is already some H has some H space structure, let's say nu. So nu is the just the H space structure means I just the multiplication of this A. And if satisfies this additional condition that rho is homotopic to nu compose one tensor del. So I'll explain what is this nu and rho for a fibration. So this rho is called holonomy action for the fibration, and so this rho is a map from F cross omega b to F, and this del is just the it is by definition rho of just fix the base point f0 of F comma dot. So that is a map from omega b to F. Okay, so on the right hand side you have F cross omega b, so it goes to F cross F, and then you consider the like HP structure, so multiplication of F to go to F, and on the left hand side you already have F cross omega b to F. So if those two maps are homotopic, then the loop space and also this loops in the loop space fibration level you have some homotopy section. That means you have the homotopy right inverse of this omega p. Then this map, which is actually already was a homotopy equivalence, that also serves as H map. Okay, so this rho and del, how they are defined. So you consider this diagram. So you have E to B, this was your original fibration. Now here you consider this diagram. So consider F cross omega B cross 0 1. So here I have to define a map. So define the map to be just x comma gamma comma t goes to gamma at t. Just evaluate the loop at t time. And on the above you just F is already included in E, so you just project the include the F in E by the projection. Then clearly this diagram commutes it at this level, because here if you take t to be 0, then gamma 0 is already the base point of b0. On the other hand, F compose like P compose this inclusion, that is also goes to your my fixed base point b0. Like F is in my definition F is P inverse b0. So this diagram commutes, and as this is fibration, we have a lift H tilde, and I define my rho to be this H tilde dot 1, and so that actually maps to E. But if I as this H tilde is a lift for H, so if I take this at the point 1, it should be equal to my gamma 1, but gamma 1 is again will be the base point b0. So that is again lies in like in particular I can say this H tilde dot 1, that is belongs to P inverse b0, which is F. So we indeed have a map from F cross omega b to F, and we define that to be my holonomy action rho. Okay, and as I already said, this boundary map is just a rho at fixed base point f0 of F. Okay, so Liu at least partially gave a condition which is how much tractable or that thing. He also gave some example of like vibration which satisfies this condition. So in particular, a result of Gania already shown that if we consider a vibration which is principal in his sense only, so then this condition is actually already satisfied. So So if F has H space structure and the fibration is some principal fibration, then this condition is satisfied. So there the usual splits that this mu compose gamma cross omega I, which is the gives the usual homotopy equivalence between those two space, actually also serves as H map, and hence this defines an H splitting in that case. Okay, so H splitting again. Okay, H splitting I missed. So H splitting is the thing that you have already this homotopy equivalence as well as the like H map. Okay, so hope that clears. So H splitting is that just that thing. So not only the homotopy equivalence, but the map is also an H map. Okay, so now in our case, so what we did, so this is a like joint thing with my supervisors, Dr. Somnath Baswa and Dr. Aritra Bhomik. So here we actually revisit like kind of get an idea from Khalil Sajab, and we actually study a um, long back like 70s thing, and from there we actually also get something which not exactly answer the age splitting thing, but at least at the homology level we have some results. So for that to define those that product, so I first need to define this whited product. So it is defined on the homotopy groups of a space. So suppose you have and alpha in pi mx and beta in pi nx, and suppose f and g represents those two elements in the homotopy groups, then the whited product of those two elements is an element of pi m plus n minus 1 of x, and it is defined to be the composite of this function. So what we do, so you think this so if we just looked at the CW structure of Sm cross Sn, so that is obtained from Sm is Sn by attaching an m plus n cell. So the attaching map is actually, in this case I'm noting by phi. So phi is a like it is just boundary of the m plus n. So that attaching map actually I'm considering as phi. Now from on Sm I already have Sm2x I have f, Sn2x I have g. So I have a map from Sm base Sn to x base s through f base g, and then use the folding map here to get to x. So this total composition map, the homotopy class of this total composition map, I define to be the whited product of this thing, alpha and beta. Okay, so the like the this whited product, this if I consider the graded like total graded homotopy groups of x, so this defines a graded quasi-Lie algebra structure on omega x, and so it has obvious properties like this is natural in a sense that if we have a map from any continuous map from x to y, then if I consider the like f induces on already on the homotopy groups, it induces map from like pi in x to pi in y. So I can consider this f star of the induced map f star in the homotopy groups. I can take the whited bracket of the alpha beta and apply f star. So that is same as you apply f star alpha and f star beta individually. So here the alpha beta belongs to pi dot of x. Okay, so on this side you also have like uh, element of pi dot of y, and here so this is kind of naturality of the whited product, and it also satisfies like graded symmetric property. Like if I consider this alpha and beta whited product of those, so graded symmetric, it's mean that you have, if you reverse the order of alpha and beta, there will be a sign. So the sign will be the like degree of alpha times degree of beta. Okay, and it also bilinear in degree 2. So bilinearity, because like pi 1 level we have like we may have non-abelian groups, so there the bilinearity uh, does not make sense properly. So that's why we need this bilinearity to like it holds in all the higher homotopy groups. And also it satisfies Jacobi identity again in degree greater equal to 2. But there is also result like some particular cases where like in the pi 1 level also we can actually get the Jacobi identity. Okay, and the last thing that we had here, that if the X is an H space, then actually all the whited bracket vanishes. And that is actually another thing, that the whited bracket vanishes like suppose this is the whited bracket of alpha and beta. Then if this is vanishes, then that means this alpha beta, this here it is trivial. So uh, so that means actually we can extend this to a map from Sm cross Sn to X, where this on if I restrict onto any like on the first coordinate, this will be F, and on the if I restrict that onto the second coordinate, that will be G. So this is a if and only condition that uh, let's say alpha beta this is 0, if and only if like there exists a let's say M from Sm cross Sn to X, such that if I restrict my M to this Sm, that is the representative of alpha, let's say F, and if I restrict my M to Sn, that will be like the map representing beta, say G, as in this notation. Okay, so for H spaces, we actually can define this M to be just the concatenate. Suppose mu is the H space structure of that space X. Then I can take this mu compose F cross G, which actually defines a map from Sn cross Sn to X. And if I restrict to any of these coordinates, so on this coordinate, if I put this simple dot, then by the H space structure thing, that this F mu compose F cross that base point thing, that will give me F, and if I put base point here in the place of F, then that will give me G. So from there actually we have that whenever we have H space, the whited product there vanish identically. Okay, so defining the whited product, we are now ready to define base product for a fibration, which is originally due to James. And the setting is, suppose we have fibration again Fe to B, and it has some homotopy section S. Then in the homotopy, for any fibration, we actually have homotopy long exact sequence in homotopy groups. But when we have a homotopy section, that long exact sequence splits into short exact sequence, and each level we have this short exact sequence from pi dot F to pi dot E to pi dot P. Okay, and here if I consider any like one element from pi I B alpha and another element from pi j F beta, then I can consider A star alpha in this pi dot of E and I star beta again in pi dot of E, and then consider under the consider the whited bracket of those two and take the image under P star. Now by the first property, the naturality property of the whited, that is same as P compose A star of alpha and P compose I star of beta. But P compose I is just a single point that is constant. So this map is 0, right? This becomes 0, and this P composes as this S is homotopy section. So P composes is like homotopic to identity. So that induces identity map in the homotopy group. So this P compose A star is just identity. So hence this is whited bracket of alpha comma 0, but alpha comma 0, that whited bracket again, that is 0. So that means this whited bracket of A star alpha and I star beta, that belongs to kernel of P star. Now by exactness, that is same as image of I star, and I star is injective. So we actually have a unique element that we denoted by this brace, curly brace, this alpha beta, with this section, this S refers to the homotopy section S, and that is an element of pi I plus j minus 1, because this is an element in pi I plus j minus 1 E, and so that should comes from again an element in pi I plus j minus 1 of F, such that the image of this element is exactly the whited bracket of this thing, and we denote that this element as the base product for this alpha and beta. So the base product is a map from homotopy groups of the base space B times the homotopy groups of F to homotopy groups of F. So in a sense, this base product actually defines a pi dot D module structure on pi dot F, okay, for given homotopy section S. And the result that we are interested in, that suppose we have a fibration with again homotopy section S, and if this base product that we just defined, if it vanishes identically, then then this map, this mu compose omega s cross omega I, hold this induced map in the homology level, that actually is an algebra isomorphism for any field K of characteristic 0. So here the algebra isomorphism means, so here this omega B cross omega F, that is an H space. So whenever we have H space in the homology level, we have an induced map, like we suppose mu is an H space, in particular this base loop space. Let's say just this is the multiplication map for the H space X, then that will induce a map in the homology level. So and now you, by Kunet formula, I can this is, and that actually defines a multiplication structure in uh, in homology level, right? So similarly, in this case, this omega B cross omega F, that is an H space, omega E is also an H space. So this map is not only a already we know that omega S as omega S is a homotopy section for the loop space fibration. So this theta map, which is mu compose this thing, is already a homotopy equivalent. So in the homology level, that is already an isomorphism, but the only thing that it is saying extra is comes from the vanishing of this base product. Okay, so if this base product vanishes identically, then we not only have the this as modular isomorphism, but also we have this as an algebra isomorphism, and the algebra structure comes from the H space. So in a sense, this uh, kind of detects a bit of structure at the homology level when we have the vanishing whited product. So the example, trivial example where we have such condition, let's say we have a fibration where the fiber is some Eilenberg-MacLane space, KGN, and if this fibration has some homotopy section S and B is simply connected, then just if we see that suppose this B, so the brace product, so take alpha and beta S, so this belongs to pi, say, so alpha belongs to, let's say, okay, BF, so this is some K B, and beta is in some KL of this thing, but only like homotopy groups here is the N. So I should consider the thing only the non-zero thing. So pi n of kgn, which is just G, right? So if I take one element from the base homotopy groups of base and another from the only non-zero homotopy groups of the fiber G, then consider the brace product of those things. So that will land in k plus n minus 1 of this kgn. But this is 0 unless this k plus n minus 1 is exactly equal to n. And if that is n, then k should be equal to 1, right? So S is non-zero unless like, or I should say other thing. So it's 0 unless k equal to 1. But k equal to, for k equal to 1, this pi 1 of b as b is simply connected, that is also 0. So in combining all possible cases, we already have this brace product vanishes just to just due to the dimension thing, like non-vanishing homotopy groups of the fiber. So we have actually enough example because such kind of vibration already appear those who have seen this Postnikov tower. So in the Postnikov tower system, you you have enough example where such kind of vibration appears. So the only thing there you need to guarantee that uh, it has some homotopy section S and the base is simply connected. Then we have enough example where the brace product vanishes, and there those cases we can actually at least say that in the homology level we have isomorphism for any field of characteristic 0. So the another like drawback of this thing is that we don't have the coefficient field to like coefficient to be any arbitrary thing, but it has to be a field of characteristic 0. In general, if we had like this is an if we had this theta as H map, then theta star is already algebra isomorphism for any arbitrary coefficient. But like we comes through this race vanishing, and we actually can't reduce this to any general coefficient, but to field of characteristic 0 only. Okay, so another result where we have the base vanishing is that, so again suppose we have fibration with homotopy section S, and suppose we have another space which is like product of some other spaces and a map from X to the base space, such that if we consider the like xk to B through this like xk included in X and through B, so if compose this inclusion of kth copy to X, this thing, if those maps are all null homotopic, then um, the pullback vibration induced by this map F, there we actually have section pullback section S as the original vibration had section. So there we also have this vibration has also vanishing vanishing brace product. Okay, so like there are enough example of space like vibration where the base product vanishes. So this is another instance. And base product in like sphere bundle sphere like vibration with base and fiber both are sphere. If there we just check for this thing that identity, if I consider the uh, identity map of SM and identity map of SN and consider the base product of those two things only, if that vanishes in this vibration, then actually the vibration not vibration as a vibration that is not split, but the total space actually homotopy equivalent to the product of those base and fibers here. Okay, so that in a sense, the brace vanishing in this case actually states uh, the splitting of this total space as brace cross fiber. So brace vanishing actually at least detects some information about the splitting of the total space. So it's like still in general fibration we are investigating that thing more, that how that thing can be like more important in splitting in loop space, and how that can help to understand the H map in general loop space vibration. And that's all I had to say. These are few references. So first one is just we are currently working on that thing and in preparation, and remaining are in the literature we followed mostly.
Thank you very much. So, is there any questions?
Okay, I can see some question in the chat. So how the map okay, I can say that thing. Okay, so here this RP map which I use to define my whitehead product. Here the thing, so this Sn cross Sn, the CW structure here is like you consider Sm page Sn and attach a m plus n disks to this by attaching map, like that attaching map. So that attaching map I'm considering as this bar P. So is this clear? Okay, and do you know what happened? Okay, so that twisted product of normal Eilenberg-MacLaurin space, that I'm not sure that
Maybe you
what
can read
happened.
the question out loud.
Okay. So the question is when the fibration, the base, like fiber is generalized Eilenberg-MacLaurin space, that is some twisted product of normal Eilenberg-MacLaurin space, then what we can say. So there we may have something, but I'm like immediately I can't say anything that what extra I can say there.
Great. Is there any more questions? No? Okay, well, that's thanks, Sandip.
Yeah, thank you.
So you can make it from the start. Stop the recording.